All right, any other homeworks? I will try to get these graded. I'm out all day tomorrow, but I'll try to get them graded before Friday. And it's most likely I will be here Friday, but there's a small chance I won't. So if I have to cancel class, I will do it through Clark's website, and you should get an email notification automatically. And I'll throw something on Canvas also, but plan on class happening on Friday. And I will do my best to be here. All right, so I get these graded. I'll get some feedback on them. I'll get them back to you, and then we'll talk about anything that I see in there. So I posted homework 2, which is due a week from today, and it's some questions from the text. Okay, so you can download the text from Canvas, and it's some questions in 3.5, 3.8, and then 3 questions on the supplemental questions at the end of chapter 3. So think about those. Think about those, and we can talk about them next time. All right, so we were starting to talk about set theory. And we talked about sets. We talked about ways of representing sets. Set builder notation, the set of all x such that x is divisible by 2, things like that. There's 2 special sets that we can talk about. So this is a set consisting of the letter A. Not a very exciting set, but it's a set nonetheless. It has a single element in it. A set that contains a single element is special. This is called a singleton set. And they hold a special place in set theory. There's an even more special set. This is the set containing no elements. And that is a valid set. A set is a collection of things. Well, it could be a collection of no things. That's totally fine. This is called the empty set. And the empty set pops up enough that we have a special symbol for it, which is just a 0 with a slash through it. And that is synonymous with just these 2 curly brackets with nothing in between. So a set containing no elements, that's the empty set. For example, the set of all x less than 10 such that x equals the absolute value of x. Sorry, x less than 0. So the set of all negative numbers that are equal to their absolute value, well, that's an empty set. There are no negative numbers that are equal to their absolute value, because the absolute value of a negative is the positive version. So this is equal to the empty set. So we'll toss those terms around a lot. All right. The other way to talk about sets is what we call interval notation. And you may have seen this before. We can write something like parentheses 1, 3. And usually, when we see interval notation, we're talking about the real numbers. But we could do it over the integers if we wanted. But let's think about it over real numbers for a moment. So if I write parentheses 1, 3, this means the set of all x contained in the real numbers such that 1 is less than x and x is less than 3. So parentheses 1 comma 3 means the set of all real numbers between 1 and 3, but not including 1 and 3. So if we drew a number line, then this interval would be everything in here between 1 and 3, but not including 1 and 3, and we sometimes show that by drawing a little open circle around those endpoints. So it's that stuff in between 1 and 3, not including the ends. And this is called an open interval. Open because it doesn't include the ends. In contrast to square brackets, which is the set of all real numbers such that 1 is less than or equal to x and x is less than or equal to 3. So on a number line, this is that stuff in between 1 and 3, bless you, but including the endpoints, so we draw filled in circles to show that inclusion. And this is called a closed interval. And these pop up a lot, so we have this special notation for representing these things. And we can also have half open or half closed intervals. For example, this would be all the real numbers bigger than 1 and less than or equal to 3. And this would be all the numbers bigger than or equal to 1 and less than 3. So we can mix and match these things. But mostly we talk about closed intervals or open intervals. And we don't really do a lot with these in this course. It's just a convenient way to represent certain types of sets. But in other branches of mathematics, you can do amazing things with just open and closed intervals. So there's a branch of mathematics called topology, and there's a version of topology called point set topology. And point set topology is nothing but the study of open and closed intervals. And just starting with open and closed intervals, you can work your way up to basically all the stuff we do in calculus. Continuity and limit points and sequences and everything else comes out of open and closed intervals. And these things have some really bizarre properties. I mean, they seem really simple, right? It's just all the stuff between 1 and 3, or all the stuff between 1 and 3, including 1 and 3. But consider this interval. What's the smallest real number in there? It's just 1, right? What's the largest real number? It's 3. Nothing too weird going on there. What about this interval? What's the smallest real number in here?
The limit is x approaches 1 from infinity?
Yeah. There's no specific smallest number here. It could be 1.1, but you know what? There's a 1.01 that's even smaller than that. Or maybe you think the smallest number is this, but you know what? There's a number that's even smaller than that. And any number you think of that you claim is the smallest number in this interval, I can quickly write down a number that's smaller. There is no smallest number. But this interval is bounded. Every number in there is bigger than 1. It's bigger than 0. There is a lower bound, but there's no largest lower bound. And that difference between closed and open intervals, that's where like our whole universe comes from in some sense. So you can get into like all kinds of weird stuff with intervals and interval notation. We won't do that here, but if you follow the dark side into mathematics, you get to do all this stuff. All right, so one other thing to note about sets. Sets are just collections of things. So I could define a set called B for bizarre, and I could say this contains a triangle, the letter 2, the integers, the real numbers, and the equation x plus 5. Is that a valid set? Absolutely. It's a set containing 5 things. Now my universe is pretty bizarre, because my universe apparently includes shapes and numbers and sets and equations. But if I define my universe to include all those things, yeah, this is a perfectly valid set. And what's particularly strange is that this set contains an element that is itself a set. But the set B only contains 5 things. How do I know? 1, 2, 3, 4, 5. Even though Z contains an infinite number of things, it's just a set. Right? My set contains a pen. Well, a pen contains, a gazillion molecules, but I wouldn't say my set containing the pen has a gazillion things in it, right? Because this is one thing. Well, Z is one thing. It's one element of the set. R is one element of the set. And I could make a new set called W for weird, and I could say that this contains the element 15 and the set B. And that's perfectly valid too. And if you say, how many things does B contain? The answer is 2. How do you know? 1, 2. Is Z an element of W? No. W contains 2 things, 15 and B. It does not contain Z. B contains Z. The bizarre set contains Z, and it contains R. But W does not contain Z. It contains the number 15 and the set B. Okay, those are some pathological examples, but they're things to keep in mind. And we're going to do some problems on the board, and we're going to work our way up to some really bizarre pathologies around this kind of thing. And we're going to get to, hopefully on Friday, the reason why we can introduce paradoxes in set theory. If we just say a set is a collection of things, if we don't restrict what those things can be, we'll get into some trouble. All right, so here's what I would like to do. We have a lot of people. We have about 30 people in here. So I have a homework set. These are pretty straightforward problems for the most part. They're warm-ups related to set theory. So we should be able to fit probably 6 groups pretty easily. Right, so maybe 2 and 3 and 1 or 2. So I'm going to ask you to break yourselves into groups of about 5 or 6 people per group. And find a spot on the board, find a marker, and have one person per group come up and pick up one of these sets of questions. So I'm going to leave these right here. So question 1 is just saying, describe a set containing 3 elements and write the set on the board. Any set you want containing any 3 elements you want. Just write it down on the board. That's your first question.
There's no board space.
Space on the left there.
I think it might maybe like
Is that a set of broccoli?
The symbol is T is a subset. That means or. So 1, 2, 3 is I know, right?
All right, so question 2. Describe the elements of the set of all x such that x is bigger than 5. And it asks, does the choice of the universe make a difference? So just describe in words or by listing some of the elements or somehow what the set of x such that x is bigger than 5, what that looks like. You can do it in words, or you can draw, yeah.
How do we want to describe it? It's impossible to describe. Any number bigger, greater than 5. That's how we explain this in words. So if x was real number, different set that x was.
So yes, the universe does make a difference. Like the elements.
What's the set for complex numbers?
Okay.
Well, wait, does that mean x is changing? Okay, so it does change.
So yes, the choice is integers. Right.
But if you have
even though they're both
Is it between 3 and 7?
okay, number
So for question 2, try to actually list some of the elements. Because I'm seeing lots of good representations of it, but try to actually list some of the members of that set.
Okay, so x is
Like list 3 or 4 elements. Number 2.
between 3 and 7.
Oh.
Between 3 and 7 is not inclusive.
I mean, right out.
Say,
3 or 4 elements.
oh no, not.
Okay, good.
So we'll just say
We're going to come back and talk about it.
Oh, I guess when we can draw it.
Now we'll do it with intervals. Describe the following intervals. So we did the first one.
You always remember to list the
First one would be
All numbers greater than 5.
or the second one. Describe it. Yeah, we can do it.
Well, we never fully
Yeah, that's what I was wondering. The other half.
So 1 and 3 would be
Nick, is this the notation that you were hinting at?
not including 2.
Yeah, so the same as like curly bracket X, colon X, that's fine.
Because you're changing the
And
so if you have including negative 1, 8, and so on, so if you have all real numbers, it's going to be 5.5 and everything else.
Describe a set as containing two other sets.
So then you can put like
Well, I guess we have to describe the set, so we'll say
So I asked you this a minute ago. We do it over the real, but we can set.
and then
Okay, I'm just gonna do 3 separate.
you can do all of them. Always do these too. Find all subsets of X. So we have, right, this is S. So what's the bidirectional subset?
Yeah, it's gonna be like curly brackets.
How many did you say?
3, 4, 5, then do the second dot, and we net.
Yeah, there's a term for this. It's called
Not the E, but the line.
not part of
Multiple is good. Alright, cool, it's good to do that.
What's the term for how many sets you can describe given a certain amount of elements, like subsets?
Power set.
Power set.
Yeah.
There's another term too I heard. It has to do with like the math of figuring that out, how many sets you could build from that.
Okay.
What's that called? I don't know. The term's eluding me. It has something to do with, not cardinality.
Well, it's related to cardinality.
It's related to cardinality.
Yeah. And we will talk about cardinality.
Because cardinality is defined as what, exactly?
For a finite set, it's the number of things in the set.
Just things in the set.
For an infinite set, it's much bigger. It's basically how big it is, but it's different sizes of infinity. And we will definitely talk about that.
So if we wanted to write every subset on this,
And we got alphas, good.
If you get too many.
Oh, we got it.
Yeah.
because order is
That was you. What? Yeah, I'm saying it does. It is what it said itself, but it depends if you do this, then you have this. It's like the same thing as Actually, lost count. Is this set technically the subset as well?
Say again?
Is a set like a subset? Okay, say you have a set 1, 2, 3. Is set 1, 2, 3 a subset?
Yes, it is. Yeah, it's not considered a proper subset, but it is a
Not proper.
subset.
So that's what this symbol means.
Yeah, yeah.
So then, yeah. We would use this one. Like this symbol. It's actually like a U. It looks like a U to me. Yeah. No, just don't write something. It's very much a U. So this is like the equal, like greater than or equals to sign. So it means it includes the same. He says the term is like a proper set. If you just have this, if you ask for the proper set, eight different combinations. How many subsets did you find? I don't know. We found 8 subsets. Which is So we can do that for the
Because the whole business is really
dangerous when you take like a super advanced class and relate.
Where's that formula?
Because you know that it's not gonna be like this.
You found it. So that's what we got here. There's 3 elements. That's a total guess.
So number of elements.
Let's try it with 1 element. 7. 1. We have 1
All right, so everybody's good on these questions, right?
No, I can see.
All right, so come on up and grab a new homework set. As soon as I... No, you can recycle them or frame them for artistic purposes.
Is it 1 per group?
All right, so new homework setup here. Come up, grab 1 per group.
Is that 1B?
Yes, so it's 1B. Yeah.
We're ahead of the game.
How many
substitutes? Fine, just 1. That one's pretty easy. Does this make sense?
Oh, no, that's not it.
How many subsets is C instead of M? Yeah, instead of all answers.
All right, I had a hardware fail.
Does this formula work for finding how many subsets you can have, generally? Because we found 8 subsets. Is this don't subtract 1?
Like lane high five.
So we may miss 1?
Yeah, there should be 8 subsets. Hey, does everybody have homework 1B?
Which one are this?
Did we like get a paper for the previous question as well?
Yeah. You didn't need it.
Okay.
Which
I was
subset
like,
are we
wait.
missing then? Because we found 8 subsets.
Yeah, 8 subsets is correct. Oh, no, sorry, 2 to the third.
Come on, dude. That's it. Oh, which would make, because like we tested the lower ones as well.
Yeah.
So if you only had 1 element, then you 2 to 1, you have 2.
Yeah, so that's where we build up in this exercise.
I'm going to lower it.
What's your head?
Yeah, I don't know. I would just.
And that.
All right, everybody working on 1B? So question 1 is like the one you just did, question 5.
Do you have any other ones for us to do?
Oh, because this is the number
Do those?
So we started with this actually. And
Oh, really?
We did most of it, and then we did the things on the board that we finished.
Okay, well, you can hang out for a bit then. So let me talk about subsets really briefly. Subset is just a set that's contained inside another set in the following sense. Let S equal the set containing A, B, C, D, and E. Let T be the set containing A and D and E. Okay? If every element in here is also contained in there, we can say T is a subset of S. And we write that with the following symbol. It's this sideways U with a line underneath. And this means everything contained in T is also contained in S. Okay, so any element of T is also an element of S. Or we could say if X is contained in T, then X is contained in S. So the even integers are a subset of the set of all integers, for example. The singleton set containing 15 is a subset of the set of all integers. And the empty set is a subset of the set of all integers, because everything in the empty set is also contained in the set of integers. This is this if-false thing again.
Is the set a subset?
And the set itself is a subset of itself, because anything contained in S is also contained in S. So we always know that S is a subset of S, and the empty set is a subset of S. So those are two special cases. All right, so question 1, just define a set containing 3 elements, and then question 2, find a subset of S. If you want to play ahead, that's where we're going. But we haven't talked about most of the stuff yet, so I don't.
What we can do.
Yeah. Yeah.
Can I substitute?
Yeah, I think S could be a subset. ABC, I think that's a subset.
Yeah, I think it's not.
Right, I think that we
Should we just leave that blank? It's not right.
We write that
what is the smallest subset?
Okay, so there's all of them. There's none.
You were listening. I wasn't.
Well, first the elements behind.
Well, the largest subset is
The set of first elements. Right. So say you have the first set.
that's a lot, right?
You have some set A, complement of A.
What else is your first set? There's three of them, like three of them. Okay. I know you have one. I want to write all of them. So, that's right. Because the definition of a subset is say that anything exists is also
Oh, yeah, I know.
Right.
So say B is, say you have a B is a set.
Technically,
One and B is not a B.
and then the smallest set of sets. This would now be because 8 is included in the one with 0. It's just that means it's 30.
He wants us to write him home. Wait, where did he come from? I mean, well, we could just do it, like, running
Oh, yeah.
includes trees.
So yeah, did you find all the subsets?
Right one.
So did you find all the subsets of S?
Yeah, C and B. The only ones we create.
What about the sets containing a tree and the four-legged animal?
Two circles intersect.
Does it have to be like
Yeah, yeah.
Oh, I thought it just meant like four subsets.
No. All find all subsets of S. Yeah, it is infinite. Well, we're gonna talk about that on Friday.
We have a whole another.
Oh, the empty set. No, so
How many subsets?
Okay, and another subset of the empty set. That's it.
Okay. And then for 9.
I get that. I don't think they're being that clever. But like on multiple side, they will like say and then they're hoping that I'm gonna like look at the got it.
That looks like a.
Wait, is that a typo? I tried to do it.
Yeah, he did all that.
Right, yeah.
This kind of.
Why is like that?
Yeah.
So basically, like that.
Do what? Which way? Nothing. Yes. What? Nothing. I feel like that's not what he wanted us to get there. That's what he said. So not including Andy, and you can only move because we said you can only move by one letter.
Is there like that makes sense.
Yeah, there is.
So what is it?
We'll get to it.
I don't think.
But it's gonna be hard with a tree of basketball on that.
I blame him. I blame him.
He's not very good I haven't taken technical.
So far, yeah.
Hey Nick, quick question.
Yeah.
So we are working on this problem. Is it supposed to be a curly bracket where it's just like parentheses?
Yes, those are curly brackets. That's a typo.
Like the, okay.
Yeah, it's a typo.
I see.
Why can't I? Wait, the set of all integers? Don't we have to have 3 No.
Oh,
See the new set.
Yep.
oh, wait. Yep. And number 9, good.
x slash y mean the complement of x inside of y?
The complement of y inside x.
So so it's a universal set is
So
so the universal set is x and x what function y is not
right.
oh wait so oh had it right so why is the universal set?
It's easier to so when we talk about y complement, we really mean the universal set minus y. What's in the universe is not in y. Right, so we're starting with that and then throwing away the other. All right, good. I think everybody's nailed this. So go ahead and have a seat and let's talk about these. Let's talk more about subsets, and then we'll go on from there. So define a set containing 3 elements, so you can pick any set that you want, right? And we got some good sets, including broccoli and basketballs, so that's awesomeness. And what?
Giraffes.
And giraffes, yeah. That's a giraffe?
I never said we were good at drawing.
Well, its neck shrunk in question 3, that's the thing. All right, and then find a subset of S and use the definition to prove that you've really constructed a subset. So let's say that that S equals A, B, C, D, E, F, G. And let's claim that T equals B, D, A, G is a subset of S. Okay, so think about our definition. Saying that T is a subset of S means if X is in T, then X is in S. That's the propositional logic way. If X is some element of T, then X must also be a member of S. So everything that's in here has to be in there. So how do we prove that this set T is a subset of this set S? Simply show that for any X, if X is in T, it's also in S. Well, if X is in T, we know that X is either B, D, A, or G. If X is B, that's in S, it's right there. If it's D, it's in S, it's right there. If it's an A, it's in S right there. And if it's G, it's in S right there. So that's kind of a demonstration proof that if X is a member of T, it's also a member of S. And that's enough to say that yes, T is a subset of S. So the goal here is not to construct a formal proof, it's to think about this definition. Okay. And then you can pick a second subset and show the same thing. And then there's the question, what's the largest subset? So I already told you that S is a subset of S, but you can come back to this definition to see if this is true. Suppose I pick some element in S. Is it also an element of S? Well, yeah. It's got to be, because I said it's an element of S. So for anything in this set, it's also in that set. That's all we need to prove that this is a subset of that. Right? And it comes right out of the definition. And then the empty set, well, if we pick some X, which is a subset of the empty set, then it also has to be an element of S. Well, any X that I pick, is it an element of the empty set? No. And if this is false, then this implication is true, right? False implies anything is always true. So I can, say X equals a square. Well, it's not an element of the empty set. So this is a true if-then statement. This says if a square is in the empty set, then it has to be in S. Well, it's not in the empty set, so this is a true statement. And for any X I pick, right, this is going to be true because this hypothesis is always false. So this is a true statement. The empty set's a subset of S. And the empty set's a subset of any set. And by both of these, we can conclude the empty set is a subset of the empty set. That's a little weird, but it's okay. All right, so then in question 6, I said find all the subsets of S. Well, S contains 3 elements. So let's go to A, B, C. And let's start listing subsets. And I think everybody found these. So you count them up, there's 8 elements in here. And we can think of this as, well, there's sets that contain no elements, there's sets that contain 1 element, there's sets that contain 2 elements, and there's sets that contain 3 elements. There can't be a set with -1 elements, and there can't be a subset with 4 elements. So any subset's going to have either 0, 1, 2, or 3 elements to it. The sets with 0 elements, well, that's just the empty set. The set with 3 elements, that's just the set itself. And so the only real work is these ones in between. Well, the sets containing 1 element each, the singleton sets, there's 1 for each of these elements in S. How do we carefully find all the subsets containing exactly 2 elements? Well, we can, do something that our brains are good at doing and say, well, we could do AB, we could do AC, we could do BC. And if we try to do BA, that's the same as AB, and CA is the same as AC, and CB is the same as BC, and we can sort of convince ourselves like that. But another way to do this, if we want a set containing 2 elements, we can make that by starting with our original set of 3 elements and saying, which element are we going to throw out? We're going to throw out exactly 1 element, and that's going to leave us with a set with 2 things. Well, how many different ways can we choose 1 element to throw out? It's just 3 ways. The same 3 ways that we chose 1 element to include. So here we're picking 1 element to include in our set. Here we're picking 1 element to exclude from our original set. So however many sets we got here, we're going to get the same number here. We're going to come back to that around week 8 in glorious fashion with something called Pascal's triangle. But we're going to end up seeing this a bunch of different ways. It's going to come up again and again and again. And it's actually already come up in Engineering 250, and so the group on the side over there with the broccoli set originally had another way of coming up with these subsets. So given your original elements A, B, C, we can define a subset as a binary number. For example, this number says don't include A, don't include B, don't include C. That's just the empty set. This number says don't include A or B, but include C. That's the singleton C. 101 says include A, don't include B, include C. 111 says include A, include B, include C. Every 3-bit number corresponds to a subset, and every subset corresponds to a 3-bit number. So how many 3-bit numbers are there? 8. 8 subsets. So this enumerating of subsets is really the same thing as enumerating patterns of 1s and 0s. And if we have 4 elements, we can associate with each subset a 4-bit string. This would be the subset A and C. So how many 4-bit strings are there? 16. How do we know that? 2 to the 4th. So if we have a set containing n elements, how many subsets do we have? 2 to the n. So there's a formula for the number of subsets of a given set. If your set has n elements, you have 2 to the n subsets. And if we have a singleton set, your number of elements is 1. 2 to the n is equal to 2. There should be 2 subsets of a singleton. What are they? Empty set and the set itself. Okay, here's the acid test. S is the empty set. The number of elements is equal to 0. The number of subsets should be 2 to the 0, which is 1. How many subsets are there of the empty set? Just the empty set. So it works. Math is good. All right, and then how many subsets of Z can you find? Well, there's a whole bunch of them. There's the even integers, the odd integers, the positive integers, the negative integers, the even positive integers, the prime numbers, the negatives of the prime numbers bigger than 15,218. There's an infinite number of subsets. But theoretically, if we were to think of the number of elements of Z as being infinity, the number of subsets would be something like 2 to the infinity. And that should make us a little uncomfortable. So infinity is a funny thing. Infinity is not a number. Okay, there is no number infinity. And so we can't really say 2 to the infinity. Infinity is a symbol we use to represent something that's bigger than any number. But it's not a number itself. It's something that's bigger than any number. So how many integers are there? There's 100 integers. Nope, it's bigger than 100. There's 1,000,000 integers. Nope, it's bigger than 1,000,000. There's 10 gazillion, skrillion, million integers. Nope, it's bigger than that. Any number that you pick, the answer to the question, how many integers are there, is something bigger than that number. Right? That's a well-defined notion, because I can count up 8 billion integers, and I can find another one. So I know there's more than 8 billion integers. So when we say that the number of elements in Z is infinite, really what we mean is not that there's some magic number that we can punch into our calculator and say that's the number of integers. We mean that there's no number which answers that question, and in fact the answer to that question is always bigger than any number that we think of. So we'll play with that more on Friday. We don't have time today, but Friday we'll do story time, and I'll tell you a story about infinity. And we will learn that there are different versions of infinity, and that some infinities are bigger than others, but a lot of them are the same size. So we'll play with that. But this question to how many subsets of Z are there, well, that's a really deep question. But we can say that there's an infinite number, right? It's more than any integer that you or I could name. Okay, let's do a theorem. Here's a fancy-ish looking theorem. A is equal to B if and only if A is a subset of B and B is a subset of A. Well, I don't know if I've given you a definition for equality. I might not have done that. Let's talk about what this means. A equals B means X is an element of A if and only if X is also an element of B. So to say that two sets are equal means that any element you think of is contained in the first set if and only if it's contained in the second. If we break that if and only if up, we can say two things. If an element is in A, then it's in B. And if an element is in B, then it's in A. And it's a little different from the subset thing. The subset says if X is in T, then X is in S. Equality says if X is in T, then X is in S, and if X is in S, then it's also in T. Well, if A is equal to B, that tells us if X is in A, so let's this is not going to be terribly formal. So proof, step 1, A equals B, that's a hypothesis. Step 2 says if X is in A, then X is in B. That's part of the definition of A equals B. The definition also says if X is in B, then X is in A. But if it says this and that, it says this. All right, conjunctive simplification. So if A is equal to B, we know if X is in A, then X is in B. Well, that's the definition of a subset. That if-then statement means A is a subset of B. That's the definition of this subset symbol. Well, we can also say if A is equal to B, right, that means that if X is in B, then X is in A. Well, if X is in B, then X is in A. That's the definition of B is a subset of A. And we've stated two things here, so we can state that the conjunction of those is true. So we can say A is a subset of B, and B is a subset of A. That's just the conjunction of 3 and 5. So we've already proven if A is equal to B, then this right-hand side is true. So we got one of those arrows. To do this completely, we need to do the other direction as well. So let's do part 2. So let's suppose the right-hand side, A is a subset of B and B is a subset of A. Those are hypotheses. And we just really work the definition again, right? If A is a subset of B, that means if X is in A, then X is in B. And that's from step 1. If B is a subset of A, that means if X is in B, then X is in A. That's the definition of subset. And so we can take the conjunction of those. If X is in A, then X is in B, and if X is in B, then X is in A. Well, that's the same thing as saying X is in A if and only if X is in B. And so if A is a subset of B and B is a subset of A, we've shown that X is an element of A if and only if X is an element of B. Well, that's the meaning of A equals B. Right? A equals B means if an element's in A, an element is in A if and only if an element is in B. So So we can say A equals B, definition of equals. And so we've proven if A equals B, then both of these subsets are, both of these are subsets of the other. And we've proven that if A is a subset of B, B is a subset of A, then A is equal to B. And so we can conclude A equals B if and only if both of these subset inclusions are true. And that's what we wanted to show. It takes way more work to write all that out than to just think about it. Right? Basically, all we're doing is using the definitions of subsets and equality. All right, so just to be really clear, are these two sets equal? Right? We know they're equal because the definition says an element belongs to this set if and only if it belongs to that set. Well, the element 1 is over here in the set on the left, it's also on the set on the right. 2 is in this set, it's also in that set. And every element in here on the right, 1 is on the set on the left, 2 is in the set on the left. An element belongs to the set on the left if and only if it belongs to one on the right. Those are exactly the same set. We can say that they're equal. And this reflects the fact that the order is irrelevant. Right? There is no first element of the set. And that's not an insignificant thing, by the way. For a lot of sets, we can define the first element of the set however we want. If we have a set of shapes, we could define the first element to be the element with the smallest number of sides, assuming there's no circles in there. So if we had a triangle and a square and a hexagon, the triangle would be the first element. If we have a set of positive integers, we could define the first element to be the smallest element in that set. If we have the set of all integers, we could define the first element to be the element closest to 0. And if there's two elements that are equally close to 0, we'll pick the positive one to be first. We can always identify an element in a set ourselves. But if you're given an abstract set, just a set of elements, is there a way to sort of choose a first element? If they're integers, if they're reals, if they're things with sides, if they're things that can be alphabetized, yeah. If they're animals, we can take the one that weighs the least. But for some set that I haven't yet named to you, are you sure that you can always pick out some particular element and say this is the first set, or the second set, or the last set? And it turns out we don't know. We have to either assume that you can do that or not assume that you can do that. But there's no algorithm we can come up with that, given a set, will let us pick any particular element of that set. And that's unfortunate because a lot of proofs involve something like let X be any element of the set. Well, before we can do that, we need to know that we can actually pick an element of the set. And you can't prove that you can always do that. You can't prove that you can't do that. So this is something called the Axiom of Choice. If you want to lose maybe a few hours or more of time, Google Axiom of Choice. And it'll take you into Zorn's limit. It'll take you down potentially a really, really fun rabbit hole. Axiom of Choice is the axiom. It's not a theorem. It's something we assume is true. The assumed to be true theorem that given a set, we can pick an element from that set. That's all it says. And you and I can do this. If you hand me a bag with 20 items in it and say, pick one of these items, I can just reach in and grab an item, no problem. But to do that mathematically, we can't prove that you can always do that. So we either assume that you can do that when we say we're assuming the axiom of choice, or we don't assume you can do that. And you get two different branches of set theory depending on whether you have that assumption or not. So Zermel and Frankel, ZF, were two set theorists who developed most of what we do with modern set theory. And there's a branch of set theory called ZF, which was developed using their axioms. And then there's a different version of set theory called ZFC, where you start off with their axioms, but you also throw in the axiom of choice. And you get to a different place. So that's just some set theory weirdness that we'll loop back to from time to time. But look up the wiki page on that if you want to see some weird stuff. And to me it's intriguing because choosing an element of a set is such an easy thing for a sentient being to do, right? Except maybe a dog. Dogs get brain locked. Like, should I eat this one or that one? But you know, you can pick something. It's not a big deal. But mathematically, it's like really staggering to try to do that. All right. So when we did propositional logic, one of the things that we focused on was building new propositions from old. In set theory, one of the things we're going to focus on is building new sets from old sets. Okay, given a set, what other sets can we derive from it? And the first one you've already done on the board. This is something called the power set. So given a set S, the power set of S, and I'll write it with a script P, this is the collection of all subsets of S. So given a set, you can form a collection of all the subsets. That's called the power set. And what you did in question 6 on the board was you basically found the elements of the power set of S. And if you throw them in curly brackets, that is the power set. So S equals a set consisting of a square and a triangle. The power set of S is a set containing each of the subsets. So the empty set, the singleton set with a square, the singleton set with a triangle, and the set containing the square and the triangle, S itself. And then this notion of 2 to the n, right? If you have a set with n elements, the power set contains 2 to the n elements. Well, we can write that succinctly by saying the order of the power set, the number of elements in the power set of S, is equal to 2 raised to the number of elements in S. So this notion, S written inside vertical bars, means the number of elements in S. And I'm going to put a note here, only if S is finite, meaning it has a finite number of elements. Because if S is an infinite set, if it has an infinite number of elements, then this would be infinity, which is not something we can raise 2 to, right? So this becomes meaningless if the number of elements in S is not an actual number. So this only works if we have a finite set, a set containing only a finite number of things. All right, so that's one set that we can develop from other sets, is the power set. And we'll expand on this notion probably Friday, this idea of the size of a set. We'll talk about what this means if S is infinite, and it does have meaning. All right, so you can make a power set. Let me leave you with, well, let me make sure it's not a homework question. Yeah, we're good. Okay, let me leave you with bit of weirdness. What is the power set of the empty set? And it's going to be a set. It's the set containing the empty set. Is this the same as the empty set? No, this contains one thing. The empty set contains no things. What's the power set of the empty set? Well, let's break it up. That's the power set of this set. It's the power set of a singleton. And it's going to be a set containing all the subsets of this. So what are the subsets of this singleton set?
Empty set. And the subset of empty set.
And the set contains the empty.
And the set itself, the set containing the empty set. So the power set of the empty set contains two elements. The empty set and the set containing the empty set. If we do the power set to the third, that's going to be the power set of this set. And it should be a set containing four things, all the subsets of this. So what are the subsets? The empty set's always a subset. The singleton set containing this first element. The singleton set containing the second element. Well, the second element is a set containing the empty set. So the singleton set comprised of just that element is this. And the final element is the set itself, whose power set we were constructing. And those are the four elements. Now, if we take the power set of that, we're going to get 16 things and lots of squiggly brackets. But we can do some interesting mathematical development just by taking the power sets of the empty set. We won't do that. I used to do that as a homework question, but I'll spare you. All right, so Friday we will talk more about making new sets from old sets. So we'll start talking about set operations, unions, intersections, complements, things like that. And we will go through another homework set that will take us into our first full-blown paradox called Russell's paradox. And then hopefully if we have time, we'll do a story time and I'll tell you about orders of infinity. So that'll be on Friday. All right, so I will see you next time.